Hello, it's Keith here, and this is lesson 67 of the platform-specific series of my 650 assembly programming tutorials. Today we're looking at interrupt-driven music. We're playing music with the ChibiTracks, my music player, and we've got the previous Mintal example here, but now we're playing some music in the background, and it's a little bit annoying, shall we say, because the pet's music capabilities are a little bit limited, but that's what we're going to be looking at today. So we're going to be really looking at how we get interrupts to drive timed music so that music plays at constant speed, irrespective of what the actual game speed is, how fast the game is running, depending on what's being done. So the problem with the PET, as with a lot of these 6502 systems, is we need to access the very high areas of memory, which are where the interrupt vectors are. But because that area of the memory is actually ROM, we can't directly access that. So we have to kind of work with ROM and hook into the ROM's interrupt handlers and then take things over. Now on the PET, we have some memory addresses that we can put our interrupt vector, the address of our interrupt handling routine, at, and they will be executed basically immediately as part of the ROM interrupt routines. However, unfortunately, the PET changed the memory addresses that we use. So with the very original PET ROMs, which is the one I'm actually using, it's these addresses that we need to use. Now, it's the 2019 address that we want to write our address, the address of our interrupt handler to. That's the IRQ address. This is the timer and the VBlank interrupt. Also a few others, but that's the address we need to change. There is an alternative one for the break command that is at these addresses. As I say, we're using the example today. I'm running on the original ROM, but the later ROMs, they change these addresses to these addresses here. So if you're using this on the later ROMs, you would need to tweak the code just slightly to make it work. Now, the firmware interrupt handlers don't do a whole lot before they pass over to the interrupt handlers that we put in place at those addresses. However, they do a few things. The main one they do is they back up the registers for us, A, X, and Y, and that's important because we need to restore them. When we finish our interrupt handler, we don't return to the interrupt handler, the firmware interrupt handler, we actually return to the running program. So we need to finish the job for the interrupt handler. The other thing they do is they check the kind of interrupt that occurred and branch off if there was a break interrupt, but basically that's it. So there we go. So that's what we're looking at today. Let's go over to our code and let's take a peek. So here's our code. So this is the file we're looking at today, pet mintal with sound. But first of all, just as a bit of a quirk, as part of this, I did have to actually look at the ROM disassembly. So I've got a copy of the ROM disassembly, which you can get online here. And we can see actually this is the interrupt handler that is called by the firmware, and you can see it pushes the accumulator, and then what it's doing here is it's actually getting the flags register off the stack here, and then it's just testing the break bit, and it's branching to the break address, which is on this version of the ROM. This is the newer version, so this is 0092, which is the break interrupt. If that's not the case though, we're jumping to 0090 here. As I say, this is the new firmware ROM, and so that is the IRQ interrupt, which is the one we actually want. Now, this is executed because that address is actually at the interrupt address at FFE here. So that is the IRQ address of the actual 6502, but as I say, that is ROM, so we can't change that. So we have to work with the ROM and get it to run our actual interrupt handler. So how do we do that? Well, as I say, it's fairly straightforward. All we need to do is write to the correct memory address of the interrupt handler here. So in the case of the ROM we're using today, in this example, we're loading the address of our interrupt handler, the 16-bit address here. We're writing it to 0219 and 021A. That would be 0090 and 0091 on the newer versions of the ROM though, so whichever you want to do. So that's installing the address of our interrupt handler. Now, just for safety here, what I'm actually doing is I'm actually forcing the VBlank interrupt enabled with E813. There is a memory mapped register there, and the bit 0 turns on the VBlank interrupt. As I say, I actually can disable this and it will work fine, but if I change this bit to a 0 here, what we're actually doing there is we're actually disabling the interrupt. And so now when I run my example, we have glorious silence, which might be a blessing because it was a bit noisy before. But anyway, as I say, that's because we're manually enabling this. But as I say, technically speaking, we can disable this, and the way it's being executed, it does actually work fine. We've got the music there, but as I say, just depending on if you want to trust what's happening before our program starts or not, you can enable or disable that as you choose. So our interrupt handler is actually at the bottom of our code here. This is what gets executed by the firmware. The firmware will branch onto this. Now, the first thing we need to do is we actually need to disable the interrupts. Now, we've got a bit of spare code here for a second example. The first example, we're using VBlank, which is going to be timed at around, I think it's 60 Hertz on this system. And so this is the best way of getting our music to play. So this is playing even if we disable this line. This is clearing a timer interrupt, which we're going to see in a moment. We don't need it for the first example. What we do need for the first example, though, is to clear what's known as the CB1 interrupt, which is more simply referred to as the VBlank. So we need to clear the VBlank and we do that by reading in from E812. If we fail to do that and we run again, what happens is exactly what happens on a lot of systems when we don't clear the interrupt. We get crazy noise because our song is playing super fast and our game never runs at all because the interrupt is firing over and over again. So the music keeps updating, but the code never returns to our actual program to show our graphics. So you need to clear whatever interrupt you're using, and this is how we clear the VBlank interrupt. Now, ChibiTracks is based on the Z80 version, so we're using zero-page entries to simulate Z80 registers, so we need to push all of those onto the stack and pop them off. I've got some macros to push pairs of zero-page entries, so H and L are 2 bytes on the zero page and so on. And of course, once our interrupt handler is complete, we need to do the work to finish the job of the firmware, because we don't return to the firmware, we return straight back to the running code with an RTI. Now RTI pops off the flags from the stack, but the other registers we're having to restore from the stack ourselves, and we have to do it in the reverse order that the firmware pushed them on. So Y first, then X, and then the accumulator, and that's what's happening here. So that's clearing up and returning back to the running program, and that's what we need to do as part of our interrupts. So there we go. Now that's how we can use the VBlank interrupt to play our music, and there's absolutely nothing wrong with that. There's no reason you shouldn't want to do that, but as learning how to do this, I did sort of come across an alternative, shall we say. We can use another kind of interrupt which also runs the IRQ interrupt handler, and this is a timer interrupt. Now what I've just done here is I've set bit 0 to 0 here, and I've sent this to E813, which controls the interrupt of the screen. And so we've actually disabled the VBlank interrupt now, so we've got no sound. Now what we're going to do this time is we're going to use an alternative kind of interrupt, a timer interrupt. Now this does allow some flexibility, because we can set a speed in 16 bits. So we can write these 2 bytes here to E844 and E845. Now this is writing 4000 in hexadecimal. This is the correct speed, roughly speaking, for the music. And then what we need to do is we need to turn off any other interrupts except for the timer interrupt. Now the way we do this is with the port E84E. Now the top bit, bit 7, defines whether we're turning on or turning off the other interrupts, and the remaining 7 bits are the interrupts themselves, bits 0 to 6. Now when we've got the top bit set to 0 and the other bit set to 1, this basically disables all the interrupts. So we've turned all the interrupts off first with that line, and then what we're going to do is we're just going to turn on the timer interrupt. So this time bit 7 is set to 1, which means enable, and bit 6 is set to 1, and bit 6 controls the timer interrupt. So we're enabling just the timer interrupt after disabling the other interrupt here. So that's what those 2 commands are doing. Now that's not actually enough to get the timer interrupt to repeatedly fire. So what we need to do then is we need to set bit 6 of E84B, otherwise it seems the interrupt just runs a single time, which isn't so handy. And so that is actually starting the timer, I think, and that's what we need to do. Now the final thing we're doing here is, of course, we're clearing the interrupt flag, which enables interrupts on the 6502. Should have mentioned that before. But anyway, as I say, if we run this now, we will get the same effect as we had before, roughly speaking. The music sounds about the same speed. Well, I'm lying. The music would sound the same speed if I hadn't disabled the clearing of the interrupt flag here. I've been hoisted by my own previous example petard there. So this is clearing the interrupt of the timer. We didn't need to do this for the VBlank, which was the previous example, but now that we're using the timer, we need to clear the interrupt of the timer, and each of the bits in E840D is a different interrupt, and so by setting all the bits to 1, I'm effectively clearing every single possible interrupt. The only actual interrupt that will occur is the timer, so if I run again now, it will actually do what I just claimed it should do, which is hopefully play the music at the correct speed. Sounds about right. It might sound maybe a little bit fast. Anyway, so that's how we can use the timer instead. And why would we want to do that? Well, one benefit is we can now have some reasonable flexibility about how actually fast we want the music to play. Let's say we've got a Super Mario game and the player's running out of time. We want to put some pressure on them and make the music faster. Well, if we change this timer to 2000 and run again. Well, that's a bit fast. It's very fast. Maybe that was a bit too much. Maybe 3000 would have been better. But as I say, the point I'm making is we can actually change the speed of the music. That's about right. So we can speed the music up but still have the game playing. So before it was playing far too fast because the interrupt was just repeatedly firing, but here we can control the speed of the interrupts, control the speed of the music. That gives us some nice flexibility. So that's how we can use interrupts in two different ways to cause a repeated timed interrupt that allows us to do things like play music at a constant speed even if our game is slowing down because there's too much on the screen. So I think those are definitely worth you knowing about and potentially using in your games. So the final thing we're going to look at is the ChibiTracks player, which is my music player. It's free, open source, and it's got a tracker of its own for Windows, which you can download. Also free and open source. Now, actually the software to play the music, we need a few things. We need the platform-specific driver. This is Chibi Sound Pro, which is the hardware driver for each individual system. There's one for each system. This is going to load in the PET version, of course. And then we've got ChibiTracks itself, and it's got two helper libraries, a tweener and fraction 16, that do the in-between calculations between notes. So I'm planning on reusing those, so I thought I'd split them out into separate modules. But this is the music player itself, and that is common to all the 6502 systems. Now, finally, we need a song, so we're loading our song in here. This is the song we're playing today. It's the Chibi Akima's theme from the original game. Now, ChibiTracks does need a little bit of memory for itself. It needs about 128 bytes. It varies depending on the system because the platform-specific system hardware needs different amounts of memory to control it, but it's always under about 128 bytes. So we're defining Chibi Sound RAM here at 3000. We're defining some variables for the actual music player here within that memory, just allocating them on the end. The player itself needs these, so we're just allocating those. We do have another few interesting things. ChibiTracks allow relocation is quite an important thing. When we compile a binary, we specify the load address, and this is hard-coded into various places in the song binary file. If we allow relocation, though, we can actually load it to any memory address and it will play fine. Allowing relocation, it makes the player far more flexible. However, it takes a little bit of memory and a little bit of processing power, so if you want, you can disable it, but that means you'll have to re-export the binary song for every load address you might want to load the file at. Not very handy for multi-platform programming. Allowed speed change is something else. We can change the playback speed of the song without messing with that timer. Again, this actually does quite significantly slow down the calculations because it has to recalculate the length of each line of the patterns. So disabling this saves a bit of memory and saves a bit of speed. Might be worth doing, and you can pre-compile the speed of the song into the binary, which stops you being able to change the speed at playback time, but it makes the file faster to play and the player smaller. So worth considering, especially on a system like this where you can control the speed with that timer. So that's definitely worth considering on this system. Finally, we've got something called SMS transpose, not very accurately named, but the master system, I had to change the pitches of some of the notes because the low notes didn't play very well. The PET also has a similar problem, so we're basically shifting all the notes up one octave to make them sound a little bit nicer. Finally, we've got a special inclusion here, PET Timer A. Now, this is actually a patch to the platform-specific music player. You see, the timer interrupt is being controlled by port E84B, but that is also being used for the music. So if we don't set bit 6 before writing to that port, we would actually stop the timer as part of our music routines, and that would kill off the interrupt. So that's just enabling a patch that we only need if we're using the timer. You don't need to enable this and have that patch if you're using VBlank, but just something I had to add in there. Okay, the last part of the equation is simply loading in the song and getting it playing back. So all we need to do is we need to initialize the platform-specific driver. Chibi Sound Pro init will start the platform-specific driver and do anything that's required as initialization. Finally, all we do then is we're loading in the song base. This load offset 0 here, that's not needed anymore. That was just some early test code that's been unfortunately hanging around. We load in the address of the song we want to play into song base. We run ChibiTracks start song, which sets everything up, including setting that offset, which is why we don't need that anymore. And then that's all we need to do. Starting the song will actually set up all of the variables. The final thing we need to do is run ChibiTracks play at timed intervals to play our music. Of course, if we were just on a title screen with a press fire to start message, we may not need interrupts, but generally speaking, you are going to want them. Anyway, as I always say, go to my website, download the source code, the build scripts, and have a go with this yourself. That's what these tutorials are here for. You're welcome to use them all in anything of your own, and I always doubt any of my examples are good enough, but if you somehow to manage to use them commercially, you're welcome to do so as well. Good luck to you. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.